about this one very specific topic tonight, which is linear spline approximation. And if possible, I hope to get through it for the one-dimensional case, the two-dimensional case, and the three-dimensional case. So I was hitting on it to a large degree already last time for the 1D case. So I will pick up there, right, summarize the essence of the 1D case. And rather than talking abstractly, I would like to go into very concrete cases. So, I mean, the generalizations you will see at home anyway, how this goes, okay, for general settings, and how it goes from linear splines to quadratic splines to cubic splines. The machinery is all the same. Once you understand the basic approaches to best possible approximations using splines, you will be able to do it for linear splines, quadratic splines, cubic splines. Except that the polynomials you deal with become bigger and bigger, okay, when you go to higher degrees. But the approach is always the same. There's another related issue that I hope to touch on a little bit. That is the enumeration of nodes or grid points or vertices in a graph, in a mesh. And this is very important. So I was hitting on that last time when we looked at the matrix that we have to deal with for computing linear splines. It was a very nice matrix, right? And because it had all the entries and non-zero entries in the diagonal. Why was it? Why is it the case that we obtain a diagonal, a tridiagonal matrix? I will talk about that, okay? It has to do with the way we index things. So, but indexing things or knots on a line is easy, right? The leftmost one is point number 0. The rightmost one is point number n. Okay, there is a natural order from left to right. The other natural order would be from right to left. Okay, it's fine too. But the problem arises in the context of scattered data interpolation. So if I take 999 random points in this room, they do not come from some nice underlying Cartesian measure, so they're just anywhere. Then the question arises, if I have a triangulation of that point set, meaning a bunch of tetrahedra, then how do I number the points? What is a good way to number points in an arbitrary mesh? Is there a best way to number things? Yes, there is. And the yes, there is related to obtaining matrices in the end to do computations that are hopefully of a bent diagonal structure where all the non-zero elements are clustered essentially along the main diagonal. And that is to obtain such an index, an indexing of the vertices itself is an optimization problem. It's not easy. Okay, and it's very, very important for all types of graph processing algorithms, for all types of finite elements computations, and for all types of linear spline approximation that we talk about. Okay, so I hope I touch on that a little bit. And there are entire books written again on just the topic of enumeration of vertices in graphs. It's important in many contexts. So I give you one particular flavor of an algorithm for that. I think let's go and see where we can push it today. So best linear splines. You don't have to copy this one because you have this one in your notes already from last time. Best linear splines. And someone remind me to stop about 5 minutes early tonight, because then I want to give a very brief quiz. Okay, so about 5 minutes before the official end, you shout. So best linear splines. Specific case. Head functions are our basis functions used for approximation, and we use uniform equidistant knots. Okay. So the setting is very simple. We have an x-axis, and I want to be concrete again. Concrete means I use this very specific case of a Cartesian mesh or a Cartesian grid. Well, it's just an integer, not set. Okay, where the x0 value is just 0, the x1 value is just 1, the x2 is 2, and the x4 equals 4. Then these basis functions over this knot partition or this knot set, they look like that. They are heads. So the first one starts here. Forget that part. We don't need that. We only want the parts over the interval 0 to 4. The next basis function is this guy. The next one is this guy. The next one is this guy. And the last one just goes up, and then the other part to the right we don't care about. So we name them based on the index of the knot over which they have their maximum. Okay, that's where the indexing for these guys comes from. So the one basis function or head function that lives above x1 meaning having its maximum above this x1 knot, is called h1. And so forth. And this guy, the last guy, is centered, even though we don't care about this piece. We don't care about this piece. This guy would be called head function 4. And this one is head function 3. This one is head function 2. And this one here is head function 0. Now, the spacing is obviously equal spacing, uniform spacing, and the deltas here are all 1. The distances between these subintervals are 1. And we construct an approximation. So this is the linear spline approximation. The linear spline approximation app, just A of x, A for approximation, is just a linear combination of these head functions. So it is a sum of 5 functions, I from 0 to 4, 5 in total, ci times the head functions hi of x. So of course there's infinitely many combinations we can produce of this stuff, and we want to produce the best possible coefficient vector, a 5-tuple, right? 5 degrees of freedom, 5 ci's, that approximates our function in the best possible way over this particular domain from here to there. That means we want to compute the best possible C value here, 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 and here. Yes, in this case, the CI values can be interpreted, of course, at the height values in this perpendicular direction, right? So what is the best possible coefficient to multiply this head? To multiply this head function, this head function, this head function, and this head function, right? It's another way to think about it. These coefficients have the meaning of, well, some height along these perpendicular lines. And where should I place these coefficients ci in the best possible way on these perpendicular lines, such that the 4 segments combined give me the best possible polyline for this curved creature. So, and then just by inspection you see that probably something like this is pretty good. Start here, go there, go there, go there, and then something like that. Okay, so it gets already pretty good. So the interpretation of the coefficients are the ordinate values in function direction, f direction. So this is my function, f of x, and this polyline, the polyline is my approximation, a of x. And so then these guys, these height values, are the actual coefficients. This is coefficient 0, this is coefficient 1, this is coefficient 4. So the function is given, the head functions are defined like this, so implicitly known, and I need to compute the unknown c's. So this is the least square step, least squares step. What does it mean? We want to minimize the integral, right, between the square differences between the polyline and the curve. So in a sense it's related to the area between these two graphs. So the solution is, in this particular case, I just talk about the specifics because the general case follows automatically for arbitrary number of head functions. It looks like this. It is the 2, 1, 1, 4, 1, 1, 4, 1. This can easily memorized. 1, 4, 1, and then it's 1, 2, right? 5 coefficients, unknowns, C0 up to C4. And on the right-hand side, you have to compute integrals, inner products between the curve and the individual head functions. So the first one is the integral from 0 to 1 of, what is it? Should I do it that way? No, because there are two basis functions that come into the picture. I don't know that. So I just say it's the inner product between the no, I can do that. It's okay. The first one is just the integral from 0 to 1 of the given function f times the first head function there, which is h0 dx. The next one would be the integral between from what is it? From 0 to 2. Why do I go from 0 to 2 now? The first one I only went from 0 to 1, but the next one I go from 0 to 2. Why is that? Well, because the domain of these functions now becomes with 2 for all the head functions in the interior of that. From 0 to 2, f times h1 dx, and so forth. The second last would be integral from, what is the second one that spans two intervals? That is from 2 to 4. 2 to 4, and the head function there, f times, what is the head function over that? That is head function number 3 times head function 3 dx. And the last one is this particular part from 3 to 4, integral from 3 to 4 of f times head function 4, h4 dx. Okay, so all the intervals here go over a width of 2. Only the first and the last have a width of 1. The rest is 0 in this matrix. And so this means this is a tridiagonal matrix. Tridiagonal matrix. Okay. And this system can be solved in linear time. What can be solved in linear time? But what might be expensive to compute? The matrix is this matrix, right? It just has 1s, 4s, and 2s in it. It's nice. If you do Gaussian elimination for such a thing, you have to do one pass or one loop going down to eliminate all these entries and make that part 0. Right? And then you have to go back up to eliminate these guys. Okay, and then afterwards you have to divide by the elements in the middle, and then you are solved. Okay, it's essentially 2 loops, and then the third loop dividing by the stuff in the middle. Okay, it's order n. To deal with the matrix, but what might be costly? The right-hand side, right? The stuff there on the right-hand side, those are integrals. The head functions are simple. The integrals of the head functions themselves, well, they are here, right? And again, you didn't correct me. This has to be times 6. Times 6, okay? You also see that these things add up to 6, okay?
Shouldn't it be 4? Like,
what is 4?
Aren't all those just unit squares, and then each one of those triangular pieces is 1/4 area-wise?
You talk about these things?
Well, so when we're talking about these integrals, it's like how much area those two segments share in common, right? So if that is from 0 to 1, then the area of each one of those triangles is 1/4, right? And so if the values in our matrix are the number of fourths, shouldn't we multiply by 4, not 6?
No. So again, I mean, I cannot go into this level of detail. But for example, the first entry there, right? You need to compute these things. And H0, I mean, with itself, right? H0. Don't copy this, okay? What is the definition of this? H0 is the integral from 0 to 1 of h0 times h0 dx, okay? Now you plug the actual line equation in there for that thing. So this thing, don't copy it, it's just, okay, giving you the hint where that comes from. This goes from 0 to 1, h0 is, what is this h0 function? It is 1 minus x, right? 1 minus x, right? Times 1 minus x. So it is 1 minus x squared, right? dx, something like that. Okay, is blah, 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 whatever that is. It is 1 minus 2x, I don't know, what is it, plus x squared. And then you integrate that thing, okay? So you end up with expressions which are sixths, and believe me. Okay? Do it at home. Use Mathematica. Okay? But anyway, because you will end up having ratios in there and fractions, you don't like those. That's why you everything, this is divided by 6 in the end. On the right-hand side, you don't have that 6, and then you multiply both sides by 6, and you only have integers here. That's why that is. And so never forget this 6. But what is expensive? Look at these guys. Are these easily computed or not? Both integrals. I said this is nice. You have a tridiagonal matrix. So what? But on the right-hand side, you have to compute what? Integrals, right? And these integrals are not easy integrals like these guys. This function f can be any function. Huh? So, for example, the first guy here, this requires either an exact way, if you can exactly integrate it, exact or approximate way for integration. Approximate way for integration right? You have this situation. You have an x, here's an I, here's an I plus 1, if I use integer coordinates, I minus 1, and here's your happy head function that looks like this. That function is just a linear function, so when I have this guy to be approximated there, well, it's a very complicated function. So this is my f of x, and this is my hi of x, right? And I need to compute this integral from I minus 1 to I plus 1, the function times the head there, head function, dx. And that's expensive, because this function can be expensive, right? So there is no way around it. You have to do some kind of numerical integration scheme here. Okay? So to compute each individual element of the right-hand side, you need an iterative scheme in general, an iterative scheme to approximate these integrals, unless the function f is simple, unless f is a polynomial in its own right. Okay, then it becomes simple. Okay, so far so good. The more general case, I want to show that again, more general, because that then will relate to arbitrary triangulations. More general, we have a non-uniform, not placement so what changes, and I also want to hint onto an optimization problem here. What changes is where we place the endpoints of our intervals. So I could have this spacing 0, 1, 2, 3, 4. Okay, it's allowed if I go to a non-uniform spacing. Now I cannot call it 0, 1, 2, 3, 4 anymore, but it's really some value x0, some value x1, some value x2, some value x3, and so forth, and the last one. And I have real deltas here, and the deltas are different from each other. So the first delta is here, here are deltas, and here's the last delta. And x1 minus x0 would be delta 0. x2 minus x1 would be delta 1. x3 minus x2 would be delta 2, and x4 minus x3 would be delta 3. So the head functions, they are no longer symmetric, but they are still linear ramps, going down linearly, going up linearly, and going down linearly, always from one knot to the other knot. These locations are called knots. Up, down, and up. Okay. And then same problem, right? Now I would like to find the best height values, the best coefficients at these respective locations. And I would get something like this. Okay, again, goal being to minimize, geometrically speaking, some kind of multiple of this area in between those two curves. The machinery is the same, except that the matrix changes. Okay, for the arbitrary delta, the matrix problem to be solved is slightly different. Well, the deltas go into the matrix. So the first one considers just the delta 0, 2 delta 0, delta 0. Next one is delta 0, 2, delta 0 plus delta 1, delta 1. Then here it is delta 1, 2, delta 1 plus delta 2, delta 2. Next one is, what is it, delta 2, 2, delta 2 plus delta 3, delta 3, and the last row is delta 3 and 2 delta 3. And that's the matrix. The rest is 0. And you see that when all the deltas become 1, as in that special case, you get that matrix with just 1s, 2s, and 4s in it. But this is a general case. Why does one have to worry about the general case, Jennifer?
Oh, I was going to ask, do we have to multiply this by 6 also?
I have to multiply this guy by 6, but I'm not there yet, right? I haven't put the right inside here. Right, but good. You're right. I should put it in front of the vector, not behind it. So it is 6 times the inner products, again, between the function, right, this is my approximation a of x, and this is function f of x. 6 times the inner products. And so the first one is for the head 0 from x0 to x1. Okay, so it's now arbitrary boundaries from x0 to x1 of the function times the head function 0. The next one goes from x0 to x2 of function times h1, and the last one is the integral over the last interval from, what is it, x3 to x4, from x3 to x4 of the function times h4. Okay, that's how that goes. Again, this is a beautiful tridiagonal matrix, it's still of order n complexity to handle the matrix, but the issue is again the using a numerical scheme to come up with the integrals, good integral approximation on the right hand side. I think I want to talk about the 2D case right away. Jump to the 2D case, so you see the generalization of all of this. Okay. Again, I stay very basic and I stay in a very simple case, namely the case of linear splines. Linear splines go for all dimensions, right? They are used to approximate curves with polylines. They are used to approximate surfaces with triangulations, triangle meshes. And they are used to approximate trivariate functions like temperature in this room, or over a tessellation of this room, using the function living in 4 space over an underlying volumetric tetrahedrization. And then it goes to all dimensions. And so here we constructed, or we used head functions like this. So we, or tend, right, have to use similar tends or platelet-related functions for triangulations in the plane. Right? There's something over the plane now, a terrain. We want to construct the best possible triangle mesh approximating the Rocky Mountains. So first you need, well, this is really scattered the way I've drawn it here, right? This is a scattered arrangement. They're scattered. There's no uniformity here anymore. It's just a bunch of points at arbitrary locations on the line. Now I have arbitrary longitude and latitude positions on a sphere, and I have height values, terrain values sticking up. And I then ask the question, okay, what are the best possible height values? These height values, the coefficients, to construct the best possible triangulation for the Rocky Mountains. And I want to do this for an arbitrary setting, right? I just want to use 1,000 longitude, latitude values and 1,000 coefficients to multiply, well, the generalized version of these head functions. What are these head functions over a triangulation, right? That's the question. Anyone knows? Anyone has an idea? These head functions are defined like what? They are defined over an interval that spans 3 knot values, right? The center one has a highest value, 1, and then they drop down to the sides to 0. So what's the generalization of that for triangulation in the plane? Something is at the center, and then you have things next to it, and something starts high and then goes to 0.
Tent.
No, we want to stick to linear ramps. Just linear. Keep it simple to linear. Linear is good. Gaussians go forever. Well, this is called the platelet, right? There's a vertex in the middle, and there's an implicit connectivity here, right? This guy is connected to that, and this guy is connected to that, right? So in the triangle case, having a triangle mesh in the plane, we have all triangles all over, and we pick a particular vertex, and that vertex will be connected by edges connecting this center vertex to its neighbors. This stencil is called the platelet, and we construct a tent over it, starting with 1 in the middle, and then going down to 0 at the surrounding set of neighbor vertices. That's the generalization of this. So, bivariate case, bivariate setting. So we want best linear splines. That's the title, the names are the same. Best linear splines for bivariate data. Bivariate data or functions for bivariate functions. Okay, first we need the notion of the head function. What is the equivalent of this guy? Okay, what's the equivalent of that? So now, the equivalent, now we deal with scattered data x, y, and f, and there's a triangulation in the plane, but I'm only interested in these head functions in a certain neighborhood, say in this neighborhood. This is just part of the triangulation. Center point. So I have this pentagon, and this is just a part of the overall triangulation. So the triangulation extends everywhere, and for every vertex, for every knot, this is the center knot. Well, I have a value at the center that is 1, and then it goes down to 0 to the neighbors. Down to 0 to the neighbors means, I have 1 here, and then it goes down to 0 to its neighbors. So the function or the graph of this function looks like that. I can construct this tent, this function everywhere, obviously, right? I do the same construction everywhere. So then this point here, or this site, is point xi. Well, it's a tuple. It is an xi, yi. Just one index, okay? I just number them from 1 to n, or from 0 to n. And this height value here is height value 1. And these guys are all zeros down here. So this is a head function defined for the platelet. This stencil of triangles, or this subset of triangles, is called the platelet, right? The set of all triangles that share the center vertex as a shared or common vertex is called the platelet of that vertex, right? So this is the head function. Head function associated with the platelet. There are different names for platelet as well in different literature. Platelet with the platelet of central side xi, of central side xi. Okay. This is all there is to it. The rest of the machinery is all the same now, from now on. Okay? We have these basis functions, we have a triangulation, we will construct the linear combination of these basis functions, and we want to approximate some terrain, right? Some mountain, the graph of some bivariate function in the best possible way, using a linear combination of these types of basis elements. But there is an issue of enumeration of the vertices. Because no longer can we enumerate the vertices from 0 to 1 in a logical or natural order. So what's given in this setting? Given a function f of xy, a function depending on two variables, and wanted, goal, to be computed. Wanted is the best possible linear combination of these head functions over a fixed triangulation. The best linear combination of the form app. Approximation is now a function also depending on x and y, and approximation depending on x and y, which is a sum. Again, I just have n plus 1 sides from 0 to n. I have from 0 to n coefficients ci that multiply these types of head functions. This guy is called head function I of xy. And I have one of these guys living above each side. Center coefficient ci times head function I depends on xy. It is different from 0 only over its associated platelet, otherwise it's 0. So formally, there is no difference between this and the 1D case, except we have one more argument to deal with. Okay, so algorithm. Well, we use these normal equations again. We use the same, formally we use the same stuff that we use in the 1D case. We have a matrix which consists of all these inner products of the basis function, the platelet related basis functions, times the unknown coefficient vector equals on the right hand side these inner products of a given function, a terrain like the Rocky Mountains, and the basis functions. So we have to compute inner products now, inner product symbol H0 depending on xy dotted with itself, H0 xy. Last one is Hn. I no longer put the argument there because the argument are twofold, x and y, hn, h0 with hn, h0 dotted with hn. And then the last element here would be the platelet above site number n, head function n, dotted with head function 0. And the last one here is head function n over platelet n, dotted with itself, head function n. Cool. Again, one can compute these things nicely, beautifully. These are just numbers related probably to the areas, right? To the areas of these triangles. Because here, these elements, the entries in the matrix were related to these areas, right? The length, the width of these intervals. So correspondingly, the integrals there will be related to the areas of the triangles. I have to compute that. But is this a tridiagonal matrix or not? Well, let's come back to that later. First, what you have to compute are the coefficients, C0 up to Cn. And then on the right-hand side, we have the inner products between the given function f and head function 0. And the last one is the inner product of the function and head function n. Okay. There is no 6 in front of it yet. Okay. This is the general formulation. Can you solve this just as quickly as in the 1D case? This is a beautiful tridiagonal matrix. Does it have a band structure? Does it have blocks? Is it a block diagonal matrix? What is it? Can you see that right away? Or does it depend on something? What type of matrix it is? What type of matrix do we want? Well, a matrix that has non-zero elements all over the place is a bad matrix, right? You just know that. So we like to have the best possible matrix. What is best possible matrix? We would like to have a matrix where, as much as we can do that, want to squeeze the non-zero elements to the diagonal, or 1 off or 2 off from the main diagonal. The question is, how do we get such a matrix? It's a very important problem in all of finite elements and finite difference computations, because you want to get the best possible matrix to stay computationally efficient. And so you can use Professor Bay's linear algebra package, right? Now there is a beautiful book, of course, that you have to read tonight. Every day read a book, read 5 newspapers and 10 journal papers. 10 journal papers, yes. Read 5 international newspapers, 1 book, 2 dissertations, 1 from your own area, 1 from some other area, and read 10 journal papers in your own area. Is Brent kidding or not? When I was your age, I had that energy. Now I have an excuse. Now I can say I no longer have that energy. So there's a beautiful book that is by Golub Van Loan. Golub, you have to read this book. It's really beautiful. Golub and Van Loan. It's called simple title, Matrix Computations. Matrix Computations. Definitely, if you want to go into an area of numerical simulation of physics, finite elements, finite difference simulation, then this book is an absolute must. Jean Golub, by the way, was the postdoc advisor of Professor Bay. So Jean Golub really was one of the giants of this whole field. And so when you look him up, it's very, very, very impressive. So, okay, matrix computations. What type of matrix is this? What type of a matrix is desirable in general? Is desirable? The answer is a diagonal matrix. If one can make a matrix, an arbitrary matrix, into a diagonal matrix. A diagonal matrix. now comes this problem of indexing things. If I give you 1,000 points here on the floor, in the plane, and I triangulate these points, then you have a naming problem, right? Whom do you call point 0? Whom do you call point 1? Whom do you call point n? Well, you can just say, this is the order the way came in. The way they came in, this was the first one coming in. It's called number 0. The next one is number, and so forth, right? But does it give you the best possible way to number the points in such a network, in such a graph? No. There is an optimal way. Okay, you have to consider all possible connectivity matrices, defining the connectivity in the triangulation that leads to a connectivity matrix where all the connectivity indicators are along the main diagonal. It's an equivalent problem. How do we get that? What's the problem? What is he really talking about? I want to talk about the problem first just for the very simple univariate case so you understand it. For the basic problem of enumerating things on just the line. Problem a best index or best indexing scheme. Best indexing. Very neat little optimization problem in its own right. And again, entire books have been written about just that topic. 1D case or univariate case. 1D univariate case. Okay. X. And I explain the problem in the context of our motivating linear spline problem. So I have these specific knots, value 0, value 1, value 2, value 3, and value 4. And I will obtain a certain matrix. The only thing I want to focus on is numbering these knots, not about the rest. Okay, these are the 5 values I have, and now I have to name them. Right? Which one is the first one, which is the second, which is the third? Well, I also have to consider these head functions. Sorry, I cannot stay away from them. The non-zero entries in this matrix that we obtain depend on the fact that certain inner products of certain basis functions are non-zero. Okay? Okay, if I call this guy x0, and I call this one x1, and I call this one x2, this is x3, and this is x4, as it was before, where are my non-zero entries? Head function 0 with head function 0 gives me a non-zero number. Right? So this is non-zero number. A non-zero number. Okay? Head function 0 with head function 1. This guy with this guy, right? Head function 0, head function 1, head function 2, head function 3, head function 4. Head function 0 with head function 1 is also different from 0 because they overlap over this interval where they are both different from 0. So therefore the inner product of them is different from 0. So h0 times h1 inner product is different from 0. But this guy, h0 dotted with h2 will give you a number 0 because it goes down to 0 and this one guy starts there. Okay, so they have they don't overlap in terms of non-zero behavior. So this will all be 0 when you analyze it. Now we go to this head function 1, with which head functions will head 1 have non-zero inner products? Well, only with this guy because they overlap here. With itself, of course, and then with its right neighbor. Head function 1 will also have a non-zero inner product with head function 2. So for this, it will be head function 1 with head function 0, head function 1 with head function 1, head function 1 dotted with head function 2, which is non-zero. The rest is 0. And the last one, head function 4, will have non-zero inner products only with itself and with this head, which is head 3. So with head 3 and with itself, okay? So then this is the general structure. And all that matters is this general structure that you obtain. Okay. All the non-zero entries, okay, are in the three diagonals. That's it. But now I do something unnatural. Now I will number these things in an unusual way. Okay, I'm only interested in an abstract sense on the structure of that matrix. So I have these head functions, and we'll use a completely unorthodox numbering. I call this guy head function 0. I will call this guy head function 4. This one will be head function 2. Maybe this one here is head function 3. And then which one is missing? This guy would be head function 1. So that means I just, for whatever reason, called this not 4. I called this not 2. I called this not 1. This one is not 0. And this one is not 3. Okay? And so this is why I'm doing that, but I want to make a point, because this is what we are faced with in the two-dimensional case. Which dot products will be different from 0? That's the only thing we're interested in. So the first one is h0 times h0 is, of course, any function dotted with itself will give a non-zero entry. So h0 times h1, h0 times h1, they overlap here, right, in this area. So therefore, this also will be different from 0. h0 dotted with h2, h0 and h2, but they are far away from each other, so there will be a 0 entry here. So now comes h0 dotted with h3, h0 and h3 dotted. Well, here's a non-zero product, so therefore here will be a non-zero entry. Now I consider the dot product between h0 and h4. h0 and h4 are too far away from each other, so therefore their dot product will be 0. You see already this thing is no longer tridiagonal, right? So I go to the next row, h1, the dot products of h1, which are non-zero. Where are they? h1 times h0, yes, they overlap, so it's non-zero here. h1 dotted with itself, of course, is non-zero. h1 dot product with h2, yes, here there's non-zero. And now comes h1 with h3, too far away, gives you a 0. And h1 with h4, here they don't overlap, it's 0. Now the next one I still do, and then I will stop because I've made the point already. h2. h2 is this guy, dotted with h0, no overlap, so therefore it's 0 here. h2 dotted with h1 is different from 0 because they overlap there. Then comes h2 dotted with h3. They are too far away from each other, so this will be 0. Then comes h2 dotted with h3 here, too far away from each other. This is 0. And now comes h2 with h4. h2 with h4, they overlap here. Okay. You see what I'm doing? I've now non-zero entries all over the place, right? And this is merely a consequence of my not doing the proper indexing. But again, on a line it's easy, right? From left to right or from right to left. Now, this is no longer, we are not happy here. Okay, this is no longer tridiagonal. Okay. Which other numbering would be optimal on the line? There are only two optimal ways, either from left to right in increasing order or from right to left in decreasing order, right? You also can call this one 0, 1, 2, 3, 4 and also get an optimal order. For the 2D case. Why is it difficult for the 2D case in the scattered setting? What is the relationship again to our problem? Our problem is this. We have to construct these inner products of head functions living over platelets, and we want the resulting matrix to be a bended matrix, a bent diagonal matrix, where all the non-zero elements are clustered to the main diagonal. That's our goal. And as I said, that's related to the numbering, how we number our sides, so our vertices. So now we go back to the problem then, the best possible numbering of vertices in a triangle mesh. And of course the problem becomes even more complicated when we talk about volume meshes. More complicated and more important. Motivation. This is the motivation, right? In the triangle, in the two-dimensional case, we have setting like this. How do we number the points? That's the problem. What is the best way to number them? Again, of course, in the context of, right, of our little baby problem here of constructing this banded matrix for linear splines. But yes, Jennifer?
Well, you probably want a way that points close to each other have numbers that are close to each other. That way when you do the dot products, they're kind of clustered.
Mm-hmm. Right.
But
good. That is, is exactly right. You want to have an arrangement where when you go through the different platelets of the different sides, those sides will have similar indices whose platelets are geometrically close, or are close to each other in the triangulation, right? Yeah, that's an objective. Mm-hmm. That is the objective. The optimal indexing might not be unique. There might be multiple indexing schemes which are all optimal in that sense, right? Multiple ways to index to come up with a connectivity matrix. This is related to the problem of finding the best possible way to number them for connectivity reasons. It's the same problem. So how do you do that? Jennifer, do you see the best possible way? Which one do you call number 0, and which one is 1 and 2 and 3 and 4? Whom do you call 0? Where do you start? You have to start somewhere. Right? I mean, on the line we take the leftmost one. What is the equivalent of the leftmost one?
you probably want to start somewhere on the convex hull of the set, because then it would have less neighbors.
You want to start from somewhere from the boundary.
Yeah.
And then grow from the boundary inward.
Maybe do like some sort of
You start here maybe? You start here?
thing.
This looks like a good start, right? Like growing a tree from the bottom.
Snake around.
So you call this 0. And then, which one is 1 and 2? You call this 0, right? This is the general idea. On the line you have like, here you started with 1 and then you kind of like, you have these waves, right? And you order them, right? Kind of like layer 0, layer 1, layer 2, layer 3, and within each layer you number them, right? Something like that. Again, there are entire books written about how to get the best best point, or get close to an optimal index. And this is the Cuthill-McKee algorithm. Very beautiful. And who is taking Professor Bai's class right now, or has taken it before? So you came across that one already?
I don't remember it.
Okay. I know he uses that. Ask him about it. So instead of defining it in its most general form, we do as I always like to do, we start with a simple example. Right? A simple scenario, a simple case. Because from the simple case you will learn the general operation of this algorithm anyway. So I give you a simple mesh. Actually, I'm making this up as we go. a nice triangle mesh, right? Very simple. Okay. The algorithm, I just have to tell you how the algorithm works. Indeed, it starts usually on the boundary. But that's not really what the initiation step is. The initialization step says pick any vertex that has minimal valence, okay, and call that point number 0. Okay, of all the vertices, you have vertices in the triangle mesh. The triangle mesh is established at this point. Find a vertex that has minimal valence and call that point 0. Then look at all its neighbors and order all its neighbors according to valence. And then iterate on that paradigm. Go to the neighbor that has minimal valence and look at its neighbors and order them according to their valence. So you go in this shell-like evolutionary process. So, and I just say this in colloquial English, and I put the structure here. Pick a vertex of minimal valence, and again, this is colloquial English. This will not be in the book by Cuthill-McKee or the paper. And then grow. I call them vertex shells. Okay, vertex shells around it. Grow vertex shells around it or from it in some kind of advancing front approach. Okay, look at all the vertices. What is the minimal valence that you see in that graph? Minimal valence is 3. Okay, so therefore you could call this 0, could call that 0, call this 0, and many others. Therefore you will get a non-unique answer, right? Okay, I like this guy. Okay, I call this point 0. Okay, point 0 is at the root of this tree. I construct the branching structure, okay? Then I look at its neighbors. Its neighbors are these guys. And I order them in increasing valence and number them accordingly. So which then is point 1, point 2, point 3? Valence 3, valence 6, valence 5. 1, 2, 3, right? This is point 1. This is point 2. And this will become point 3. Okay? So vertex 0, the first level, is producing 3 children on the next level, which are called 1, 2, and 3. Right? From left to right is the order according to valence at that level. 1, 2, 3. Okay. Now, I go by this order, 1, 2, 3 in that level, and look at the children they are producing, again, by looking at their neighbors that are not named yet, don't have an index yet, and order those unnamed neighbors in increasing order of valence. Number 1 has still one unnamed neighbor, this guy. Okay, this guy will become number, what's the next number available? 4. 4. So 1 has one spin-off, is number 4. Okay, that's it. The next one is point 2, vertex 2, has still unnamed neighbors, namely these guys, this one, and this one. And they will be numbered in increasing valence. This is valence 4, valence 3, valence 6. 3 being the smallest here, valence, makes that guy the next point. 4 was the last number, so this becomes number 5. This one becomes number 6, and this one then has to be number 7. So 2 is producing 5, 6, and 7. 5, 6, 7. 5, 6, 7. Now point 3. Point 3 still has one neighbor, this corner guy, which is unnamed. Okay, so this one is another square on the same level with all the other squares measured, right? And what will the name be for this guy? What's the name? The next number, right? 8. So 3 is producing 8. Okay, we have the next level. Now again, we look at these vertices and their neighbors and number them. Point 4 is done. There is no neighbor. Or 4, not named yet. There's the end. 5.5 has just one neighbor, right? Now I use bullets again, okay? This guy. 5 has one unnamed neighbor. The next number, not used yet, is number 9. So 5 produces 9, and that's it. Only produces 9. Here's 9. 6.6 doesn't produce anything. 0.7 has one neighbor, this guy, which will be number 10. So 7 produces 10. 7 produces 10. And 8, what is 8 producing? 8 has two neighbors, not yet named. Right? This edge connection, so this guy and this guy. So last number was 10. So now we number these according to valence. This is a valence 3 vertex, a valence 6. So this one is the next one. This is 11, and this one is 12. So 8 is producing 11 and 12. 11 and 12. Okay, so that is the next level. Okay, now we go from left to right again. 0.9. 0.9 has no neighbor any longer. That is not already named. 0.10 has one neighbor, not yet named, this guy. And now I use circles again. Okay, this is then 0.13. So 10 is producing 13. 10 produces 13, and that's it. 10 and then go 11. 11 produces one guy, this one here, which will be 0.14. Okay, 11 produces 14. And 0.12 induces the index of the last available vertex, which is 0.15. Okay, so 12 produces 15. Okay. It's just beautiful, right? It's beautiful. So now we can see these shells, what I call shells here, these shells evolving. So here was my first one, initial one. The other one are these circles. The next level or layer or shell is the one consisting of squares, which is this guy. All right, we fix it. It goes all the way down to the 8 here. Huh? It goes down to the 8. Let's fix it. That's good. You get it. This might be my last figure on the board. Huh? Better make it beautiful. Okay, fixed. All right, so just meandering around a little bit widely, so it's okay. Okay, so that is the next layer. Now comes the layer of bullets again. So here, these guys. And the last one is here. And of course, it was first the intuition that guided the invention of that algorithm, right? They wanted to have this kind of layer structure, right? Like peeling an onion, wanted to build this. That was the intuition behind it. Everything comes from a nice, cool geometrical, constructive intuition, and then ultimately they formalize it. So, I mean, when you go to the paper of Cuthill-McKee, I think it is 67 or 68 paper. Many of you will remember it from high school. Then the formalization comes from a very simple idea. Everything always goes back to a simple idea. Of course, we start with a simple idea and we formalize it. And then, being computer scientists, we think of it as building this tree structure, right? And it's indeed very simple. This is the tree you construct. Pick minimal valence vertex, this guy, or you could have picked one of the other corners, yeah? And then you grow these layers around them, layer by layer. Go look at the neighbors, look at their valence, and order them in increasing valence. That's it. And this produces something that is very close, heuristically, empirically demonstrated, being very close to the optimum, or n optimum. But again, there are more expensive algorithms out there that really give you an optimal solution. Okay? For some applications, you want to get the optimal solution. So you could call this shell 0. I mean, this is my terminology, right? Shell 0, this would be level shell 1, and this is shell 2, and so forth, right? So this is shell 0, this is shell 1, and this is shell 2. Do that. How is this related again, Jennifer, to the beauty of that matrix now?
All the ones that are close together in terms of neighbors and close together in terms of numbers will produce things clustered towards the back.
Yes. So now we have this third dimension here, right? These platelets, these functions over those platelets. But this guy, for example, this one is a platelet for 0.6, right? So there is this tent sticking out the board. And this tent here will only have non-zero inner products with its neighbors, right? And so the neighbors should therefore have indices which are close to the number 6. Okay? You want the neighbors of number 6 to have numbers which are close to the number 6, and not numbers like 1,000, 1,200, 4,800, because those things would be done. Okay? So that was the principle. So if we look at the structure now, in terms of the inner products, again, it's just the structure that you're interested in. The head function over this platelet consisting of just two triangles, right? There's a head function 6 out at 1 here, and then goes down to 0 here, and goes down to 0 here. These two triangles. So head function 0 will have non-zero inner products only with itself and with head 1, head 2, and head 3. Right? And we'll have inner products of 0 with all the others. So head function 0 will have a non-zero inner product with itself, with head function 1, with head function 2, and with head function 3. That's it. Right? The other head functions are too far away because these tens have a finite domain. Okay, the rest is 0, meaning I don't have to even indicate what it is. Not indicating anything means 0. So now let's look at the head function 1. Head function 1 sticks out here and then goes down to 0. Right? Goes down to 0 at vertices 0, 3, and 4. With which head functions does head function 1 have non-zero inner products? So let's see. Head function 1 and head function 0, yes, they overlap, so here's a non-zero entry. Then you have head function 1 with itself dotted. Of course, that is non-zero. Then you dot head function 1 with head function 2. Is it 0 or non-zero? It's 0, okay? Because their domains are too far apart. That's a 0, okay? So, but I said for zeros I don't even have to make a symbol. And then comes head function 1 with head function 3. Yes, they are connected. They're edge connected. This goes back to the connectivity thing, okay? So head function 1 and 3, well, there's an edge there. So therefore, it's non-zero. Anything else? 3 and 4? Yes, right? 1 and 4, yes, of course. There's an edge connecting them. 1 and 4, now 1 and 5. 5 too far away. 6 too far away. 7 too far away. 8 too far away. It's all 0, okay? Anyway, at the end of the day, you will see, what will you see? That the inner products for this huge matrix that you produce doesn't lead to a huge matrix after all, that it leads to a matrix that will be banded. Okay? Non-zero inner products all along main diagonal. And that's great. What is the maximal bandwidth there that will be ruled by, think about that. Huh? I know I have to stop. Shoot.
Does this algorithm rely on us using the min-max triangulation?
No, not at all. This is completely abstract. This doesn't really use, this algorithm then doesn't consider geometry whatsoever. It only considers the graph, the triangulation.
It kind of
It
seems
only
like...
has points that are connected by edges. There's a connectivity there, but it doesn't have the points don't have a number yet. They don't have a name. So the naming, the numbering, the indexing is still to be done. That's all. X, Y locations go in, and connectivity between the X, Y's goes in. So that's they define a valid triangulation. And then you produce a best possible, if possible, a best possible indexing scheme.
It seems like the effectiveness of the algorithm would depend on that, though, on how good your triangulation is.
Yes. So there is a best possible triangulation, of course. Yes. When is a triangulation good? Because the matrix that I get, you're absolutely right. How large can the bandwidth be? That is related to the maximal valence of all the vertices. So that's another thing that we would like to keep, that we would like to keep threshold limited. Okay? The best possible triangulation in 2D is this. This is the best possible triangulation in 2D, obviously, right? The B's have already figured that out in the dual sense by knowing the Warren diagram for it. This is the best possible triangulation because every vertex has valence 6, except those on the boundary, which are valencies even smaller. Okay? So yes, if you have a triangulation where you have a vertex in there that has a valence 100 and is connected to 100 neighbors, that means that this vertex there will have at least 100 non-zero inner products with all the neighboring tens in its neighborhood. You don't want that because that screws up the bandwidth, right? It gets very big then, at least 100. So therefore, you would like to also construct a triangulation where not only the triangles are fat, meaning having 3 times 60 degrees, but also where if you can possibly do it, keep the valence of the triangle mesh under 6. Okay? So these are the different optimization criteria for triangulations. Triangles should be nice in terms of the geometry. They should be nice in terms of their valence behavior. Should be nearly the same valence everywhere and not to exceed 6 if possible. And they should be triangles that approximate a distance, right, from the geometry or the function to be approximated. These 3 optimization criteria sometimes are in conflict with each other. And either you get nice triangles and larger approximation area, or you get a smaller triangulation area but ugly skinny triangles. Okay, so good. That's it. All right. Now I have to give an assignment to you, the quiz. Okay. You all have the laptop with you? You need your laptops now. Okay. Those of you guys who have the laptop, the quiz is you have to do these student evaluations. Okay. So I have to tell you that those of you guys who have the laptop available right now and have it handy, please, because this is a graduate class, you get notified about this, right? You have to do that. If it was an undergraduate class, I have to hand out these the sheets. But because this is a graduate one, you get notified automatically. Do this. This is very important, okay? Okay, so class is over for me. I no longer have to talk. Next week, you guys will talk.